Section 3, we're going to get into the atom itself here. And I want to point out that when I was a student, I remember my teachers telling me that we would never see an atom. And there's no law in science that says that we can't directly detect them. Now, they're so tiny that light doesn't bounce off of them as individual atoms, and so then we don't actually get to see the atom itself, but we can use something like a scanning microscope, or I believe that this is not actually a electron microscope that's being used here. Restate that, atomic force microscope. And in that situation, we're actually going through and kind of just feeling the individual atoms. Then the color is added in later on artificially because it doesn't actually have color down at that level. But we're going to get into the atom and the pieces of the atom. Now, some of the pieces, is actually a law in science that says we cannot detect those pieces because they're too tiny. It's not just that we haven't built a good enough detector yet, it's that we can never build a good enough detector. Essentially, and this is a horrible oversimplification, but trying to detect it is going to move it and disturb it such that we can't actually directly observe it. As we mentioned in the last section, all the elements are just different types of atoms, and atoms are the smallest particles that retain that characteristic. They are made up of smaller pieces, but if you pull one of those small pieces out of an aluminum atom and then that same small piece out of a hydrogen or out of anything else, those small pieces are the same. They're indistinguishable. Not that we really can, but if you were to pull those out, swap them, put them back in there, the one would go back to behaving like aluminum, the other would go back to behaving like hydrogen or whatever it was, and so those pieces are indistinct. So even though they are made up of smaller pieces, they lose their distinction at that point, and so we don't really focus on them. Plus, they're not stable on their own. They always end up coming back together to form an atom of some element. Originally, the idea of the atom came from the Greek atomist who kind of just did thought experiments, and they imagined that you could take something and you could cut it up into a tiny piece and cut that into a smaller piece, and you could keep cutting each of those pieces in half, and you'd eventually end up with this tiny little indestructible piece that you couldn't destroy. And that's actually what the word atom means, is indestructible. Now, that is similar to something called Zeno's paradox if you get into philosophy, or there's some areas of math that touch on infinity that get into it. And the idea was close, but they imagined that you could get to this indestructible piece of water, an indestructible piece of wood, an indestructible piece of stone. And of course, that's not the case. Like, I don't know if they thought that there was indestructible pieces of humans, or they realized that humans were made up of the different pieces, but it's kind of like, where do you say that that is now the piece that is the thing? Is it the bone, or is it the parts of the bone, the marrow and the outer bone? And so there's the right idea, but there's no experimental evidence for it, and they completely ignored the fact that you could get combinations from other things, that you didn't have to have wood atoms to make wood the element. Anyway, Dalton based his idea off of that. I want to say that he originally published in 1804 and not 1808, but I'm not going to test you over that. But he proposed that atoms were why we ended up with certain combinations. That is why hydrogen always bonds to oxygen in a 2-to-1 ratio, or that calcium always bonds to carbon, always bonds to oxygen in a 1-to-1-to-3 ratio. And so those ratios that had been discovered already by another chemist a few decades beforehand, he then argued that the atoms are responsible for those proportions. And so he had a tiny bit of experimental evidence there, but we're not directly detecting the atom. He then came up with his atomic theory, and his atomic theory said that all matter is made up of atoms, that atoms of an element are identical to one another and different from other atoms. Not to say that there can't be similarities. The alkali metals all have similarities with one another, but they are also different from one another. He said that atoms of 2 or more different elements combine to form compounds. There are some compounds, things like O2, that aren't different elements, but are still something that is at least a compound or a molecule. Things can bond to themselves, but that the compounds are made up of these atoms bonding in whole number ratios, and that you get the same ratio of numbers. And so if you have a 1-to-2 ratio, then if you have a million of this one, then you have 2 million of that one. That's what it means here by the same number. And that chemical reactions involve the rearrangement of those atoms. That atoms are never created or destroyed in a chemical reaction. And that is true. About the only one that he had that was wrong is that he did say that atoms could not be broken into smaller pieces, and that one's been thrown out. I'll also say I don't think he numbered them. He just kind of made these assertions, and people have come up with their list. And so I've seen people arrange these lists ever so slightly differently. The numbers on the list don't matter. The ideas on the list do. And atoms are never created or destroyed in a chemical reaction. They simply rearrange, and that is true. And it will come up again later on in chemical reactions. It'll show up as the law of conservation of mass and matter. I will say that we have figured out ways to destroy atoms, and we do that essentially with another field, physics. There's an area of physics and chemistry that overlaps as quantum mechanics, and in that we can actually break down those atoms, but it's not from a chemical reaction. It also means things that the ancient alchemist idea that we could turn lead into gold just isn't possible, because if you start with lead, you end up with lead. You can rearrange the lead and make it bond to different things, but you can't ever get the lead to turn into gold or vice versa, because you start with certain atoms and you have to end up with those same atoms. Fast forward about 100 years, and we start to discover the subatomic particles. Sub means smaller than or beneath. Atomic means atom here, and so we have inside or under the atom. Particles that are inside the atom. Protons, neutrons, and electrons are what they are. You've hopefully heard of them before. I will point out that we tend to abbreviate them in chemistry with a lowercase letter and then a superscript sign that has the charge on it. And protons happen to have a positive charge. Neutrons are neutral. You got to be careful on that. It's neutral starts out the same as negative, but our negatively charged piece is the electron. I found students get those two confused. If you remember there's three pieces, then we can't just have purely the two opposites, positive and negative. There's got to be something else in there, and the in-between is actually no charge. And they were discovered because those pieces had charges. Now, of course, the neutron doesn't have a charge, and so it was the last to be discovered. It was the hardest to discover because it doesn't have a charge. Quick review of charges here real quick, that like charges repel, and opposite charges, or unlike charges, attract. Students usually don't have a problem remembering that opposites attract. I've seen that they a lot of times forget the word repel. And I remember when I was a student in 8th grade, someone in my class raised their hand and asked my teacher, like, why did they have to make it hard? Like, why did they not make it such that the same ones attract one another and the opposite ones repel one another? Wouldn't that just be easier to do? And my teacher was like, yeah, that's a good point. I don't know why. And it's a ridiculous point. Science is not about telling nature what to do, usually. It's about trying to describe what nature does. If you take two positively charged pieces and bring them together, they repel. If you take two negatively charged pieces and bring them together, they repel. If you take one positive and one negative, they will attract one another. It's just what happens. Now, that one was asked in the context of magnets, but it's the same thing. And magnets actually get their properties, if you want to get down to the nitty-gritty of it, from the spins of electrons. we're going to get into how each of those pieces were discovered, and the first one is J.J. Thomson's cathode ray tube experiment. Now, the old-style TVs, the ones that were really boxy and had the very curved screen out here, instead of our flat screen TVs that are both thin and actually flat on the front instead of curved, those are actually called CRT TVs, cathode ray tube TVs. And what it is there was a tube in here that was really what was connected to this, and that tube had an electromagnet going around it, and it had a charged plate here. Well, that charged plate was negatively charged and would actually cause electrons to pop off of this, and they would be steered, caused to change directions by the electromagnet here, and so then we could cause them to hit different parts of the screen, and then they'd light up what were called phosphors that were coating the screen, and those phosphors would glow different colors, and then that is what would give you your image on the screen. However, what Thomson did is he simply moved a magnet near them, knowing that a magnet could deflect them, and any way he moved it, he could only detect these negatively charged pieces. But it was known that the atoms themselves were neutrally charged, that they had no charge. And so what he imagined is that there were these negatively charged pieces in there that were like plums in a plum pudding. Now, what the Brits call pudding, we would call cake. So this is, you have to imagine like a raisin bread, or I like to think of this as a Jello with fruit in it, that you have these negatively charged pieces in there that are in his case, plums, and another one, blueberry muffins. Your blueberries there are the negatively charged electrons. But since he couldn't detect the positively charged piece in there, then that surrounding goo had to be positive, and it had to be a bigger positive to cancel out with all those little small negatives, such that the atom ended up neutral. Well, part of why it was hard to detect those positively charged pieces is, first off, this plate that he had here was only ejecting electrons. It wasn't ejecting the whole atom. Two, those were tiny. The protons are all in one area, and so they're this really densely packed positively charged nucleus, and that was discovered in Rutherford's gold foil experiment. What he was actually trying to do is he was trying to measure the size of the atom. So if we back up here to this model, the thinking was that if he had a positively charged piece that he could send through the atom, well, here it might wobble around a little bit as it gets attracted to the electrons or repelled by the positively charged goo, but those positively charged pieces would mostly pass all the way through. However, if you could get that positively charged piece to hit a region out here on the edge where there weren't any electrons, where you only had the positively charged piece, then it's going to get deflected, it's going to repel, and it's going to move out that way. And then by doing some math, by actually being able to detect where these things hit out here on some kind of detector screen, you could figure out essentially a triangle there, do some trig, and figure out then from how big the deflection here is, how big the atom itself here must have been. And so he is at least trying to come up with what's called an upper bound, where he wanted to say the atom is at least no bigger than this. Now, why, when he did his experiment, he had the fluorescent screen all the way around it? And I will say I have never seen it drawn like this. I have always seen it as if the ring was flat on the table, and I'm pretty sure that's how it actually was. But he had the source of what are called alpha particles, and alpha particles happen to have a positive charge. It was known at that time. Turns out the alpha particles themselves were the nucleus of an atom. They're actually one of these tiny nuclei here. They're specifically the nucleus of a helium atom. Again, we'll get to that in chapter 5. But then they would hit the screen here and light up the screen, and as this is kind of what he was expecting. Now, the only reason I can guess that he put this all the way around it is maybe he was trying to prevent other particles from being able to get in, because we get alpha particles, beta particles, and other radioactive particles coming in from other places. So maybe he's trying to keep those from getting in. The other possibility is that they kept getting flashes on the edge of the original ring, that they had a small ring. They got flashes there, and like, oh, we need to make it bigger because we're getting these flashes flashes, and then they make it bigger, and then they make it bigger, and eventually get to where essentially it wraps around everywhere except for where they need this beam to be able to come through, and they're getting these deflections that they expected most of them to not deflect, but on occasion they would get these extreme ricochets where it would come in and go way out. Well, the only way that a positively charged piece would do that is if there was some kind of positively charged piece down inside of there that was real dense all in one place. He said that he was surprised by doing this as if he had fired a cannonball at a sheet of tissue paper and it bounced off. So what it meant is that there had to be a region of densely packed positive charge in the nucleus. And so now we've discovered the protons. We previously discovered the electrons. Well, we know that protons and electrons have opposite charges and they're going to be attracted to one another. So what should happen is if the positive charge is there and the negative charge is out here, it should just be attracted in. Turns out when a proton collides with an electron, you actually get the other piece, a neutron, and so then they would actually cancel one another out, and so that can't be the case. And so instead what must be happening is the electrons aren't getting pulled in, they must be moving around, and if they're moving around, then they're orbiting. Well, if they're orbiting, then they can't be slowing down. If there's something there, they would have drag and they would slow down, and then they would eventually spiral into the nucleus. And so if they're not slowing down, then the surrounding space must be empty. And most of the atom, over 99% of it, is empty space. That means the atoms that make you up are mostly empty as well. And the reason things feel solid is because of those charges on the outside edges repelling one another. An atom then has a nucleus, a center, that contains the protons and the neutrons, and the electrons are in a region around it that are mostly empty space. Now, you'll notice that we did not go through and explain how the neutrons were discovered, and as I mentioned already, they are a neutrally charged piece, so they were hard to detect because we couldn't deflect them with charged things with magnets. And the experiment, because of that, is a little bit complex to explain. You're not going to need to worry about it anyway. The two important ones really are Thomson's and Rutherford's, not to say that there aren't others that were involved, as well as discovering other details. One big one that stands out is the size of that charge, but that's not something we're going to worry about right now. Anyway, this here is lithium metal, and then of course a zoomed in view here we can see individual atoms, and then a zoom in on an atom here. The diameter of an average atom is somewhere around 10 to the negative 10 meters. That would mean that we're looking in the nanometer range. For metric prefixes, that's 10 to the negative 9. It also turns out there's another measurement unit called an angstrom, where because atoms are so close to having a nice, neat 10 to the negative something number that's slightly off of our 3 jumps that we do for the metric system, we said, why not come up with one that's on a 10 to the negative 10? And so there's 1 times 10 to the 10 angstroms in 1 meter as another conversion factor. We won't have to worry about that much though. And within the size of the atom, you'll notice the nucleus is super tiny. It is 1 10 to the negative 15th. That's a 10 to the 5 difference. It is 1/10,000th the size of the atom. And yet the majority of the mass is there in the nucleus. The protons and neutrons have most of the mass, which is what our next one is about. So we came up with one, since they're so tiny, we came up with a new measurement unit simply called the AMU, Atomic Mass Unit. And it turns out that what we did is we said that the atomic mass is equal to 1/12 the mass of a carbon atom that's made up of 6 protons and 6 neutrons. And so then 6 protons, 6 neutrons, that's 12 pieces. And so then you divide that by 1/12, or multiply it by 1/12, which is divided by 12, and then we say it has a 1. Now, it turns out that the protons and neutrons themselves don't exactly have masses of 1. They're essentially 1, but there is a slight difference between them. The electrons are very tiny mass. It's about 1/2000th, and you don't need to worry about what their exact mass is, but it is very tiny by comparison. Their size is also tiny. It's to a point where we don't actually know what their size is. There's an interesting paradox that's there, but nucleus makes up most of the mass of the atom, the electrons make up most of the size. Here then is the summary of this information. We have their abbreviations, their charges, their masses, and where they are in the atom. Great picture here. I will point out that this one here would be lithium, with only having 3 protons, 4 neutrons, 3 electrons. We'll get into how you know that soon-ish. Found outside the nucleus, that's the electron. Positive charge, that's the proton. Has mass but no charge, that is the neutron. True false statements here. The mass of an electron is greater than a proton. That is false. It's the opposite. Protons have a positive charge, electrons have a negative charge. That is true. The nucleus of atom only contains protons and neutrons. That is true as well. I will point out that because there's positively charged pieces and neutrally charged pieces, that means the nucleus is positively charged. And that finishes section 3.